All right, so we got our sample wedge calculations. So anytime we're doing any of these calculations or simple machine problems, make sure you have a calculator handy and your formulas packet. For our wedge formula, we're looking right here at this diagram. So this is the type of diagram that you're going to be drawing. And you can see our height, or h, or some people might call that the width of the wedge, is going to be the bottom part of the equation for IMA. So if you look at IMA is dE, or effort distance, over dR, or resistance distance. So we can equate dE to L, which is our length, and dI to H, which is our width. So keep that in mind as you're doing any wedge problems. So here is our example scenario, and this is actually one of my own, and I kind of mixed up the numbers a little bit, but this is actually a scenario that I have at home. So I heat my house with red oak logs for firewood. While wood is not a uniform material, red oak logs require a maximum of 1,000 pounds of splitting force to split a log into usable firewood. So what that means is that most logs won't require 1,000 pounds of splitting force, but they could require up to that. So the especially tough ones might require that much. Most will be less, but that's what we're going to work with, the 1,000 pounds. So I use an 8-pound maul, which, if you are unfamiliar with a maul, it actually looks a lot like a sledgehammer, except for the end of it is a shape of a wedge. And I use that to split my wood. The wedge part of it has a width of 4 inches and a length of 10 inches. With a wedge with those dimensions, how much force must I generate to split the most difficult of pieces? So first thing we're going to do is we're going to sketch out our wedge. So a wedge, a standard wedge, is going to look just like in the diagram right here. And I'm going to label, right here is my L, which I'm going to also say is equal to dE. And then right here is my H, which is equal to dR, or resistance distance and effort distance. So we can do a couple of things at this point. Let's start out by calculating our IMA, or our ideal mechanical advantage. So our ideal mechanical advantage is L over H, or dE over dR, as would be the case for every single simple machine. So if we take those measurements, and again, I didn't finish annotating this wedge over here, so my width, or H, is, where is it at? 4 inches. So 4 inches, and my L, or dE, is 10 inches. So IMA is equal to 10 inches over 4 inches. And if we punch that into our calculator, 10 divided by 4, we get 2.5. So this wedge has an IMA of 2.5 to 1. So what we want to find out here is if I have a resistance force of 1,000 pounds for my toughest piece of wood that I need to split, how much effort force do I need to generate using this wedge to split that? So now I'm going to come down here and I'm going to do my static equilibrium equation. So static equilibrium equations are the same for every single simple machine. So I have effort force times effort distance, and I'm going to set that equal to resistance force times resistance distance. And now I can just substitute in the values that are already knowns and solve for the one that isn't. So I'm trying to figure out how much effort force I need in order to split 1,000 pounds, which means that I'm solving for my effort force, or Fe. So Fe times my effort distance, and my effort distance is on my diagram right here. So effort force times 10 inches equals my resistance force, which I said my maximum resistance force is 1,000 pounds, times my resistance distance, and my resistance distance is 4 inches. I'm gonna just put a slash through that there, I miswrote. So Fe times 10 inches equals 1,000 pounds times 4 inches. So then I'm going to start to simplify. So Fe times 10 inches equals 4,000 inch-pounds. And now we want to isolate Fe. So in order to do that, we'll divide both sides by 10 inches. This side cancels out. And this side, the inches cancel out, so our answer is going to be in pounds. So Fe equals 400 pounds. So my ideal effort force, or the effort that I need to generate in order to split that log that requires 1,000 pounds of force to split, in a perfect world, I need to generate 400 pounds of force. That sounds like an insurmountable amount, but I can tell you that when you are swinging an 8-pound maul, that is actually possible. So that is an example problem of calculating effort force required with a wedge. So right here are a couple examples of a wedge. So right here on the left, this is called a maul. Some people call it an axe, but it's actually a maul. And you can see that it is kind of like a sledgehammer, except for one end of it is shaped like a wedge. And you use this as a wedge to split firewood, which I'll demonstrate in just a second. Right next to it here is actually just a wedge. So this is used to also split wood. And right next to it, I have a little mini 2-pound sledgehammer that you use to pound this wedge into wood to also do some splitting. So here's the maul in action. Here we have our splitting wedge in action.